Well, welcome to our first example of applications of waves. We're going to stick with 1D, which is following up on our intuition video. Later we'll move to 3D to have a more general setting, but then I'll do a lot of the calculations in 1D. Main calculations in 1D, but we'll also look at 3D. So we'll flip back and forth. But let's do 1D following on transmission lines. Voltage and current is equivalent to EX and HY from the previous video. Now, what I'm going to do is I want to get a second order wave equation here. It's very similar to what we did in class before. I'll differentiate this with respect to Z. And this with respect to T. Now, you can see that this is the same as this. You say, well, wait a minute. It's not the same because here we differentiate Z second and T first, and here it's the other way around, but the two are the same. So this is the same as this. And if that's the case, we can take this and substitute it in here because these are the same. So we take this and stick it in here. This is the second derivative of E with respect to Z is equal to mu naught epsilon naught. And mu naught epsilon naught is 1 over V squared. Now in phasor form, if we represent this in phasor form by writing EX is something like this. So we can say that for phasor, EX of Z and T is equal to EXS, e to the j omega t. We substitute in, and we're going to get this d squared, EXS dz squared is equal to, of course, this brings down j omega twice. The exponentials cancel out. We've seen this before. We get minus omega squared over v naught squared times EXS. And this we call k naught squared. So this is equal to minus k naught squared EXS. So what's the solution? Well, we've seen this before. In fact, this is a total derivative. So to be strictly correct, it's not partial, but not partial, because there's no other variable here except for Z. We've seen the solution before. EXS is equal to, we're going to deviate a little bit from the book's notation because we want to emphasize forward and backward going waves. So we can write this as E x naught plus times, well, it's exactly the same as the transmission line solution. We're going to have minus j k naught z. And I'm getting tired of talking. Sam, what's the next term going to be?
Well, it's the return wave, right? So E x naught minus.
Yeah, E x naught minus.
E to the, well, it's the different direction. So flip the sign here, j k naught z.
All right, Sam, the big challenge for you now is we've got to write the magnetic field. We could use the curl. We could use Faraday's equation to do it in phasor form.
That's a lot of work.
It's a lot of work. So what do you suggest?
Well, we have this conversion factor here, right? Why don't we just use what we learned from transmission lines?
Okay, so do you want to write the transmission line first and then substitute in, or do you just directly want to go for HY?
Well, let's start with the transmission line one and remind what people are.
Okay, so I think there's enough space. Maybe you can write it here and then.
Okay.
There you go.
Sounds good. So in transmission line, when you have the I phasor.
Yep. You're going to run out of space.
I am. I'll write small.
Okay.
V plus divided by Z naught.
Right?
E J omega T? No, beta Z.
Beta Z. We use beta instead of K. Beta before the book switches back and forth. Same meaning here. Will be very clear as we go what we're talking about. So K naught is like beta. Same units, wave number. Okay, go on.
Mm-hmm. And then in the book, it talks about the reverse in polarity in the current. So there's a minus return voltage. E plus J beta Z.
Okay, we
there's a
just
Z
squeaked in there.
Yep.
Okay, so now let's see if we can write down, given the variables here, what's going to be in here. Maybe you could use, we're not going to have Z naught, right? We're going to have this thing here, which is the impedance, intrinsic impedance, as before. So by analogy, what's going to go in there? What's the equivalent of L?
Well, so L becomes mu naught. So I assume we do the same here. Mu naught divided by epsilon naught. Is that correct?
Yeah, that's exactly right.
Okay.
So now we know that eta naught will go in here, and I'll let you do it. Remember, the amplitudes are this.
Okay. So for HY, S, start with the equivalent of V plus, so E plus X
0,
S
X
Oh,
0.
no,
That's just the
X naught.
amplitude. Yeah.
divided by eta naught.
Now we're going to
E.
have that.
J Z
Yep.
minus, because of the minus sign here. Well, that right's very small here. Eta naught
Just give lots of room for the exponential.
Z.
JK naught. Boy, that's going to be really squishy there. So you can see this is E and this is H. It goes exactly from the transmission line equations. Well, we didn't have to do all that. We could have just written it down from scratch. But it's nice to see everything being worked out.
Yeah, the analogy is important.
The analogy is really important. Now, there's something that we have to consider, and we'll see that in the next video, and that is the waves often go through material that's not a vacuum. Here's a vacuum. And so the waves actually travel through material that has both capacitance and a bit of resistance. And so there's some ohmic things going on here. We want to know how they're going to come about. And we're going to redo this example when we have actually, horror of horrors, a complex number for epsilon naught. So let's see how that goes in the next video.
I don't look forward to that.